Yeah, I would like to follow up a little bit of what Tom talked about regarding the origin of organic rich terrains on Ceres, and I would not dwell onto the details of how we get to these organics on the surface. That is ongoing work, and hopefully we'll be able to report on that soon. But for now, the focus is this intriguing region on the surface of Ceres. Here you see a bird's eye view of the so-called Ernotet crater. It's about 50 kilometers or so across, and these reddish regions that you see is where the organics has been detected. So we will talk some more about this. The first point that I would like to make is that it appears that Ceres really is a chemical factory. And so these are amazing results from the Dawn spacecraft, and most of this comes from the near-infrared spectrometer, where we're actually able to observe observations of absorptions of a number of interesting compounds. And you see here a quick list. We have phyllosilicates, some of which are ammoniated, then all the way to various carbonates, magnesium rich or sodium rich or even calcium rich perhaps, and then some salts as well. So this is a very intriguing composition that has been inferred from the spectrometer, as I said. But the focus for today is actually the aliphatic organics. These are compounds that contain the CH3, CH2 group, such as kerite, for instance. And here is also a little molecule that shows what kind of compound perhaps we are dealing with. And in the molecule shows, of course, in black are the carbons and the spheres. The black spheres are carbons and the white spheres are hydrogen. So this is the kind of material potentially we are dealing with. And so let me give you a little bit more details about the actual detection, because this is important, whether or not we can really strongly rely on what has been said. As we already discussed early on this morning, sometimes the observations are not unique, are not obvious. So here is a case, I believe, where the observation of organics, and particularly aliphatic, is remarkably strong. At the center, you have a number of spectra from the Dawn spacecraft. Those in white are from regions that do not appear to have large amount of aliphatics. Those in green comes from this region, the Ernotet region. And the interesting feature here is the feature at the center, the 3.4 micron absorption. That's indicated by the letter A. And now this feature is going to be mapped in panel A on the left. So the left shows the distribution of aliphatics as inferred from an absorption and based from spectrometer. So it's pretty, as good as it gets from remote sensing. I also want to point out that there is another interesting correlation of feature. Of course, that is the carbonate absorptions at 3.9. This is shown in the chart by letter B. And in panel B on the right, you actually see the distribution of carbonates in the very same location. The reason I want to bring this up front, even though I'm not going to be talking about carbonates later on, is because there is a spatial correlation between organics and carbonates. And that's intriguing, and of course, it's going to play an important role in understanding how these organics were formed or deposited at the surface. All right, let's now have a slightly different view. This is yet sort of a summary slide, but again, I want to show you the overall location of where the crater Ernotet is located. It is in the northern hemisphere of Ceres. The reason I want to stress this, because as Tom Friedman previously mentioned, this is one unique location on Ceres where we do find a significant amount of organics. There are perhaps a couple of other spots, but the detection is kind of ambiguous there. So this is really a unique feature. And so now, of course, the question is how we can explain this. The inset, the larger map shows the distribution of organics, again, based on the spectrometer. And the inset shows an actual framing camera picture of the same crater, which has a much higher resolution. This is the highest resolution that we get, something like close to 20, 25 meters per pixel. Now, in the camera picture here, we can only go after visible colors, and so the coloration that you see here is inferred from visible colors. But it's nice to see that this reddish material actually correlates with what the spectrometer sees in terms of absorption. So this is an overview of the region of interest for today. I also want to present a couple of slides as introduction again of what kind of organics we may expect to see on an asteroid or dwarf planet like Ceres. And so if you look around other asteroids in the belt, we certainly expect to see lots of organics, and not because there has been, I would say, a direct observation of that, but just because we have lots of carbonaceous chondrites that are inferred to come from the main belt. And if you look at the carbonaceous chondrites, you clearly see absorptions at 3.4 micron, pretty much the same kind of absorption that we see on Ceres. You have Murchison, Yvonne, and Renat, so these are type member meteorites, and all they show these absorptions to aliphatics. Likewise, compounds like kerite or asphaltites, these are terrestrial organics, also show the absorption. And again, just to make it clear, this absorption is due to the stretching of the CH3, CH2 group. So this is the feature that we are interested in. Well, organics are certainly not present only on asteroids. We also have comets that happen to cross every now and then the main belt, and so it's also interesting to have a quick look at comets. When it comes to the detection of organics on comets, there has been a huge amount of work, primarily coming from the coma of comets, right? Because that's where the detection is easier. There is not much, as up to my knowledge, of an actual detection of a cometary nucleus, perhaps except for 67P, which is perhaps the most well-known case. Now, in this case, you see an absorption 3.4 micron that comes from a spectrometer on board Rosetta. Now, it just happened that this is basically a copy of the spectrometer that took data for Dawn. So those two measurements are really comparable in terms of resolution and sensitivity of the instrumentation. But however, what you will notice now that these absorptions it's very broad, and it doesn't look like aliphatics at all. In fact, there's been a couple of works that are mentioned and are quoted here that they conclude that the feature we are looking on 67P at least is due to the group CO2H. So it's not necessarily the kind of compounds we see on Ceres. So if you want to make a connection with comets, you need to be careful, because although comets contain lots of organics, they may be not the same kind of organics that we see on Ceres. So with that said, let's try to speculate a bit more about the origin of organics on Ceres. Generally speaking, we can come up with two sort of end-member scenarios, where the first one on the left is exogenous origin. That means that the organics were not native from Ceres, but instead they've been delivered to Ceres. And so in the little cartoon I have, it shows like an impactor, presumably organic rich, would collide with Ceres and deliver organics. So impactor could be an asteroid, could be a comet perhaps, for what we just discussed. The other end-member scenario is that instead the organics are endogenous. That means they were formed within Ceres, and so presumably they are present in the crust of Ceres, and then perhaps an impact could have mobilized the organics and brought this material at the surface close to the Ernotet crater. That is where will be observed the organics. So we have these two sort of end-member scenarios. Now, either way, it doesn't matter which one you prefer, but you realize that cratering is going to be an important process, either in the form of delivering or in the form of excavating organics. And so we need to worry about how this process would work. So what Tim Bowling and I did was look a little bit more at the what kind of organics could preserve a collision process. And so this has been done in the following way. It's well known that organics, and in particular aliphatic organics, are subject to thermal degradation. So in other words, if you heat them up a little bit, carbon-carbon bonds can break, and groups such as CH2 or CH3 can be lost. These are relatively volatile, and if you lose those groups, you will basically suppress the absorption, and so it becomes harder and harder to find them at the surface. This process has been studied by Kawabuka et al. In the lab pretty extensively, and they come down with a formula like the one I indicated here that shows the concentration of organics as a function of time due to heating, and you see T stands for temperature here. So it's a process where you have to carry on and understand what the temperature and for how long you are heating given organic to count what fraction might survive. And we do this now coupling with shock physics code simulate the collision. And so in the next slide you will see, hopefully, yes, you will see the first scenario. So that is impact delivery of organics. So I'm not going to show the details of shock physics simulations. I'm just going to give you the results. How to read the plots. This is what I call the marble plot for obvious reasons. What these spheres indicate are 4 different impact scenarios. Impact parameters are indicated on top, so we have the velocity, the impact angle, and the size of the impactor. And so we have 4 types of collisions here colliding with Ceres, and then we track, assuming that there are organics on the impactor, then we track what is the fraction that actually survives the thermal degradation process that I just described, and that is color-coded. So let's start first with this blue case where it would be relevant for a cometary collision onto Ceres. As you see, the impact speed is 10 kilometers per second, which is appropriate for a comet colliding with Ceres. And as you see, the impactor is all red, meaning no organics would survive. Now we can look at the other cases. These are lower impact speed. That is sort of the average collision among asteroids. And so this will be the case of an asteroid colliding with Ceres. And you see there are cases in which, like the one on the right, in which no organics would survive. But I'll drive your attention on this case in the middle here where perhaps some organics would survive. We're talking about something like 40% of the initial budget of organics may survive. But also, I'd like to explain why that is the case. This is only because we are considering an extremely grazing impact collision. It's only 30 degrees with respect to the surface, so it's a very grazing collision. And furthermore, it's also a small impactor. The fraction of organics that survives is also a function of the impactor sizes, and if you increase the impactor sizes, the fraction drops. And so you basically, in order to get this delivery to work, you need to have a crazy impact and a small impactor, and a low velocity. There are other issues as well with this scenario. Let me briefly mention a couple of those. Well, first of all, the impactor is not going to be 100% organic. So if 40% is the fraction that survives in this simulation, you have to convolve that with whatever amount you start with, perhaps 5%, like in the asteroid carbonaceous control. So basically, you drop down to below 2%. And so you need to consider that there is a dilution effect because the impactor material is going to be mixed at least by a factor of 10 with target material. And so this will drop down the amount of organics clearly below 1%. And so then it's not detectable anymore. So bottom line, we conclude that it's unlikely for organics to be delivered on Ceres by this process. And of course, we also now to look at the other aspect of the problem, that is impact exhumation. Is it possible that organics in the subsurface actually survived and were deposited at the surface as we see them today? So here is another impact simulation that shows basically the impactor here Notice now it's much larger impactor because this collision is now set in order to reproduce the large Ernotet crater. So the final crater that will be formed here is about the size of Ernotet. What the plot shows here, we do not show the final crater. It's just we just show the temperature field that we produce in the target. And so these little arrows show the streamlines. So in other words, all the stuff that is in gray here, it's material from Ceres that's going to be excavated and eventually will redeposit the surface of Ceres. And again, the color coding gives you the fraction of organics that would survive. So as you see, there is a hot spot at the center close to the impact point where organics are totally destroyed. However, stuff that's going to be excavated, is not heated enough for the organics to be destroyed, and so they will survive. So we have shown with this modeling that organics that are potentially present in the subsurface of Ceres would survive the process. The other interesting aspect about this is that you can pay attention to the Y scale. We are basically able to excavate a few kilometers down and yet be able to bring that material close to the surface. So this is another interesting way of what kind of mixing we can get in this process and yet preserving organics. So the conclusion here is that based on the observation, lab work that shows that the aliphatic compounds are subject to thermal degradation, we then conclude that it's unlikely that these organics on Ceres were delivered by impactors. It seems more likely that they were basically formed within Ceres and then redeposited and redistributed at the surface by collision. So in other words, the aliphatic organic on Ceres may be native to Ceres. Now this, of course, brings up a bunch of interesting questions that I do not have the time to address today, also because it's still ongoing work. But the first question that ties back to Tom's talk is how much carbon there is on Ceres. This is a very important question. The other question is whether or not these aliphatic organics were synthesized within Ceres, or maybe not, were simply concentrated close to the surface by whatever internal process. So this is still an ongoing question, as well as, of course, the wider implication for the transportation and delivery of organics in the inner solar system. So with that, I'll stop here and take any questions. Thank you.
Thank you. We have a question here at Survey Central. Excellent talk, Simone. Thank you.
Yeah, that was very interesting. This is Dale, and I have a question about the, going back to one of your early slides, since you extracted the profile of the 3.4 micron structure, I'm wondering if you've actually tried to model that with the 4 components that are known to be in there, namely the symmetric and asymmetric modes of CH2 and CH3. The reason that's worth doing, in my view, is that if you can derive a value for a CH2 to CH3, the number of bonds, then you can compare that with the interstellar value, which is of order 2.5. It's the very kind of thing we're trying to do with the organic signatures on the Saturn satellites. And it's challenging, but you have such a nicely defined spectral feature there, it would be really great to model that by decomposing it into the 4 components.
Yes, that's an excellent question, and I have not done the spectrum modeling myself, but I do believe that there are a couple of groups at least that are looking into this. I'm not sure this has been published yet. Probably it's been submitted, I would guess. And so yes, this is something that is going to come up. The first spectra that were published were perhaps a little bit too noisy to do this. To tearing apart the 4 components, as you said, but I believe we have improved that, and so hopefully that is something that will be published soon.
I'll look forward to it. Thanks.
And I'd like to add on to that. As I was looking at that plot you showed with the comparison, you had 3 or 4 things in there. Murchison was one of them. What struck me is the CH3, the very first dip that you see in the spectra, is stronger in Murchison than it is in a lot of the other things that you showed. And in all of the laboratory materials that I used when I was trying to fit the interstellar medium, I was really struck by the fact that Murchison fit better by far than anything that we could come up with in the lab. And it was primarily because of the strength of the CH3 band. And so I think that's trying to tell us something. Like maybe there was more methane to start with, or so, I don't know what, but something. And so I too was wondering if you were able to model by comparison, but I was thinking try comparing it directly to Murchison first.
Yes, that's a good point, and I believe this is part of the ongoing work, in fact.
There are a large number of comments that have been typed into the chat room, and I'd like to read them if that's possible. The first is from Andy Rivkin saying that there have been direct measurements of organics on asteroids on 24 summits by Rivkin, Emery, and also by Kempines et al. I think that was to make a note of that, I guess.
Is that Tammy's?
Yes.
All right, thank you.
And then Stephanie Getty states it is important to consider whether the local environment is oxidizing. Is it important? Whether the local environment is oxidizing or reducing. She could imagine thermal processing to lead to volatilization in the presence of oxidizing environment compared to the potential for polymerization or aromatic catalysts possible in reducing environment. I probably misread that terribly, but I hope that was okay.
I guess that's it's pertinent to the formation of the organics, perhaps, in which case oxidation states could be important. We haven't done that part of the problem yet, I believe, but I agree that that's an important aspect that we need to consider if we want to come up with an idea how these organics formed. As I said, it could well be that we start off with some CI material or CM, for instance, and which they do contain these aliphatic organics. And what we see on Ceres is just the fact that they were concentrated in one spot without requiring any additional chemistry or formation. It's conceivable, I think, but it's also conceivable that they were synthesized within Ceres, starting from raw building blocks, in which case then the oxidation state comes into play somewhat.
She had a later statement saying, to clarify my question, I'm asking about assumptions of the mechanisms at play when looking at thermal degradation of impact organics.
Okay, the degradation was discussed in the Kukubo paper that I mentioned. And my understanding, it's a very complex and dense paper, but it's a very nice paper. And the kinematics of the degradation is not necessarily very well understood. That's my take on it. But I would defer to the paper for that. There is also a comment from the room here.
Does that mean you're using degradation of IOM? That paper's on Murchison IOM, right?
So what they did is, and Tim Bowling, who did the implementation, I can comment on that. Please, Tim, go ahead.
Murchison IOM and bulk Murchison.
Interesting. Okay.
Yeah, and what they did is took a spectra of the IOM where they see the 3.4 micron absorption, and then start eating up the sample and do the measurement again, and they will notice how the absorption would disappear after a while. And so they were able to use that information to back it up, sort of a degradation rate for the concentration of organics based on some assumptions on the kinematics of the process. As I said, it's a very complicated paper, but it has a lot of details.
Okay. Another comment from Jeff C. Regarding impact destruction of organics, most of the infall is likely to be small, largely fractal grains, and they hit regolith grains comparable to their own sizes. How does that affect the survivability of incoming organics?
So if I understood, this is related to delivery of dust material instead of large chunks of large asteroids or large comets, right?
I think he's adding some more to this question for me to read. I'm not certain.
Yeah, if that is.
So not the large. It's not large things hitting a slab, is what he says.
Yeah. It remains to be seen whether or not most of the mass delivered is from dust grains or instead of larger asteroids. The take we had for this first analysis is just realizing that there's so many craters at the surface that it was conceivable that some of those craters and impacts were organic-rich asteroids or comets, and so we just wanted to see whether or not we can do that. Let me also mention another part of the problem that I didn't talk about in my talk, and that is related to the geological settings of where we actually see the organics. It's very localized. If the organics were delivered through a dust, a dusty component, then obviously the distribution of organics will be uniform across the surface. And so then it's not obvious why we should end up with just one spot where we see organics, because you would expect a more uniform distribution. Of course, there's lots of craters on the surface, but it's not like the regions that we are interested in. It doesn't lack craters. It's actually extremely, there's craters everywhere. So if there was an early delivery of dust, it could have been mixed in by all those collisions as well. So bottom line, why then we should get this very fine, localized deposit? That's something else to consider.
Okay, Carly asks, what then is the process to get the organics to within a few kilometers of the surface?
Yes, Carly, I was expecting the question, and unfortunately, I don't have an answer. I don't know. I don't know what that might be. I believe there is Julie and others on the teams, but also other groups are now looking into this, are looking at what kind of chemistry we may have in the interior of Ceres and what are the processes that could deliver this close to the surface. But I do not have an answer. It's just amazing. As you know, on Ceres, we see lots of interesting surface features like ahunamons that would require some sort of vertical migration of material. So there is observation to claim that there is vertical transport. Whether or not that plays a role in the organics, I don't know.
Okay. Diane Wooden asks, carite is spectrally most similar, but carite is rich in aromatic bonds. Can you comment about the aromaticity of this material compared with the aliphatic emphasis in analyzing the spectra that you showed?
Yes, I'm afraid I cannot comment on that. The carite was just a convenient terrestrial sample that was used for the spectral modeling. It is not to say that carite is necessarily on Ceres. In fact, I believe Hannah here has done some work in this regard, so I will let her speak on this.
So I'll be talking tomorrow a bunch more in depth about the spectroscopy portion of this, and I have spectra of insoluble organic matter from the meteorites, which show that nice strong 3.38 micron band that Yvonne was talking about, and would argue that carite is maybe, while it matches the spectral shape in some ways, is maybe not a relevant material to use. So I'll talk a lot about that tomorrow.
Okay, let me give you one last question from the chat room. From Damanveer Garwal. What do you mean by, and if I mispronounced that, I apologize. What do you mean by endogenous in previous generation of exogenous? So why would organics have survived in the impacted body itself?
I'm not sure I understood the question.
What do you, let me try again. Somebody speaking?
No, I'm trying to guess. So with endogenous, I mean organics that were formed within Ceres, so to speak, and in the crust of Ceres, and they simply were mobilized by collisions. That okay. Is the, I don't know if that's answered the question.
Wait a minute. I'll get a clarification on this, and then I'll move on to the next paper, if that's okay.
Sounds good.
Well, we've got some more questions in the room here.
Oh, okay. Go ahead.
This is Kelly Miller. I think in your impact model, you said you were using a dunite impactor, and I'm just curious as to how dependent your conclusion about endogenous versus exogenous organics and their survivability is to the porosity and the density of the impactor that you're using.
Yes, that is a very good question, and I will have Tim answer to that. He ran the code, so
it matters, but not enough to affect the conclusion. Oh, sorry, yeah, it matters, but not enough to really affect the conclusion. So we can use a different composition like salt. We don't have that many shock-ready equations of states we can use, and dunite is a well-characterized one. So the composition matters a bit. You get more heating actually depending on what composition you use. But porosity also matters because you get hotter impactors. So if you have a porous impactor, you actually get more thermal degradation.
Oh, is that right?
Yeah, if anything, this could be a relatively conservative kind of estimate in that regard. Yeah.
If you have a porous target, it's more complicated because the area where you're destroying basically all of the organics right beneath the impact point is smaller. But in any case, the entire impactor is heated a lot. And when you have a porous impactor, it's heated even more.
Okay, so if you were to take something like a 67P-like composition where you've got 50% ice, 50% rock, and a whole lot of pore space in between, it would reach the same temperatures, but probably higher.
Yeah, and the impact velocity for something like that is going to be a lot higher, and that matters as well. So.
Cool. Thanks.
I had a question too. So you're basically thinking that these aliphatics were exposed in an impact. But I've never been quite clear about the distribution of the feature.
Yeah.
And whether where you see it strongly is related to anything that looks like material that's been dug out.
Right.
I don't understand it.
Yeah, the logical setting of the feature is it's complicated. There are, broadly speaking, this reddish material is distributed in proximity of the rim of this one large crater, Hermotet. I'm not claiming that necessarily Hermotet is the crater that excavated this material. It could have been prior craters that have done that. Then if you go in and zoom in at a much smaller, you will see that there are smaller craters that they have a very reddish ejecta blanket, and that implies that these smaller craters are also excavating perhaps organics that were in the subsurface there. So yes, it's a very complex geological setup here.
Okay, so how long do you think the organics have been exposed?
Excellent question. My understanding is that the organics will not survive, that long at the surface once they're exposed. So, but what the time scale is, I don't know. It could be a giga-year, it could be less. That I don't know, but I would like to find out because that would add additional constraints of when all of this happen, perhaps.
But maybe you could place constraints on it by looking at those little craters, right? It sounds like
the little craters could be extremely young.
Yeah.
There is no way of knowing. This crater that you see here, the Hermotet crater, is probably a billion years old.
But that looks like it doesn't have anything to do with that.
Can I make a comment too?
Yeah.
If you look into, I think it's who's it? Brown who's working.
Carly Peters.
Yeah, Carly Peters has been showing that when you zoom in and you actually use the framing camera data and use band ratios, that these organic features, she thinks, relate to younger, fresher craters, so they've been recently exposed. So you could have a large region that's organic rich, the organics at the surface space weather away, but then landslides and small impacts excavate smaller subsurface material, throw it up on the surface where
That's also true. Pretty young. But having a good time scale for the degradation of these organics at the surface will be useful. And I don't know if there is such.
For the carbonization. Yeah. Right?
Yes.
Yeah.
But not for. I don't know. I don't know if there are other processes that could remove the absorption.
Yeah, I think it would be carbonization.
Okay.
And I think that understanding the time scale, that's really important. We don't have good experimental data on that.
Okay, cool.
I am ready to move on to Dan Britt's talk on carbon and meteorites if we can.
Well, then,